all of these derivatives that we're going to deal with in related rates are with respect to time, and the variables that we're taking the derivative of are spatial variables like x and y. So we're going to use implicit differentiation a lot here. But the hard part is, don't write this down because I'm just, so, up to this point we've been looking at functions that relate the y coordinate to the x coordinate. We draw a curve. And that's more like driving somewhere from here to, from Clifton Forge to Covington. We've got a certain what I would say path, but path's not the right word. Anyway, we go a certain way every day. That's our trajectory. That's our coordinates. But what we're interested in here, and if we look at the derivative, that's more like the direction we're moving. So if we're moving west, that's kind of like zero slope. If we're moving east, it's zero slope, and all the different directions we're moving, that's the slope of the tangent line dy dx. That's the direction we're going. The actual coordinates are where we are in space. But it really doesn't tell us anything about how quickly we get from point A to point B. So to talk about how quickly we get there, we have to take the derivative with respect to time instead of with respect to a dimension or distance. So that we'll skip all of that stuff. And it's, as I said, it's important in engineering. So let's look at an example here of how these problems work. So if we drop a pebble in a pond, you get concentric waves going out from the point where the pebble is dropped. If the waves are moving outward at a rate of 1 foot per second, at what rate is the area, that's the area of the circle, increasing when the waves have reached a radius of 4 feet? So you can see we're given some information. We're usually given some rate information, or we've got to calculate some rate information. Depends on, they could give us the rate of change in the area, and we could figure out the rate of increase in radius. We have to get one or the other. So what we have to do is you have to come up with an expression that relates expresses the geometry of the problem. In this case, the geometry of the problem that relates the two things. One is the radius. This is a radius. This is the distance from the center where the pebble is dropped to the wave is going to be the radius of the circle, and the area is just pi r squared. So our geometric relationship that we're going to use in this problem is area equals pi r squared. So let me just write that down. So we need the geometric relationship, some geometry. So they're usually things like areas, volumes. The Pythagorean theorem gets used a lot, relating the hypotenuse to the two sides. That's the biggie. In this case, we're starting off with the geometric relationship that the area is equal to pi r squared. So to find the rate of change of the area relative to the rate of change in the radius, we take the derivative with respect to time of each term in the equality, just like we did the other day when we were doing implicit differentiation. There, what you had was one of them we did implicitly, the y part, and one part we did explicitly, or just normally, which was the x. So again, if we have an equality and we do the same thing to both sides, it's still an equality. So the derivative of the area with respect to time, what you get is the derivative of a variable is 1, but because it's implicit differentiation, you get 1 times dA dt. Now in this section, we usually don't use the prime, because prime typically means the derivative with respect to x. And because we're if I put a prime, is that the derivative of a with respect to x or r or t? So we're going to use the other form of the derivative where you have the ratio of dA over dt. Then the left-hand side, pi is a constant, so we just pull that outside. And then the derivative of r squared, the derivative of r squared is 2r, but we have on the end our implicit part, which is just, before it would have been y prime. In this case, it's going to be dr dt. So this is the equation that relates the rates, the rate of change in area with respect to time, with the rate of change in radius with respect to time. And once you get to this point, you go back and you say, okay, I think I should be given all the information except one thing. So what they're asking for, at what rate is the area increasing? Well, that's already on the left-hand side. So we've already solved for that. Sometimes when we take the derivative, the thing that we're trying to solve for might be on the right-hand side, and we have to do the algebra. In this case, we don't have to because it's already been done. I'm just going to rearrange these terms, 2 pi r dr dt. Again, it's usually put constants first, and if you have a rational number, you put that first. If you have some kind of irrational thing like pi, you put that next. Then you put any variables or polynomials, and in this case, the derivative term is the end. And what we should find is that we know everything in the problem. So let's read the problem. If the wave is moving outward at a rate of 1 foot per second, so that says that dr dt is equal to 1 foot per second. So that's the rate of increase. And notice it's moving outward, and outward means plus. That's another thing you have to be careful about is the information they're giving as a negative rate of change or a positive rate of change. Because this is getting bigger, it's a positive rate of change. Okay, so that's dr dt. And it says, what is the rate, at what rate is the area increasing when the waves have reached a radius of 4 feet? So the second piece of information is that we have 4 feet. And you see that the two unknown quantities in this problem are r and dr dt, so we just plug it in. So you get 2 pi times r, which is 4 feet, times dr dt, which is 1 foot per second, and you'll get 8 pi feet squared per second. So it's kind of like physics in that units are important. And it makes sense because area is in meters squared or whatever, it's in length squared, in this case feet squared, and time is in seconds, so the result should be in the correct units, which it is. So the rate of change of area with respect to time is positive 8 pi feet squared per second squared at a radius of 4 feet. If we did 8 feet, then we put 8 feet in here. This thing would still be traveling out at a certain wave speed. This stays constant. But this, as you get to a larger radius, the outer waves, the rate of change in the area gets larger. Okay, so that's kind of the basic concept. So we had to figure out what the geometry of the problem is, take the derivative with respect to time. At that point, we usually are given all of the pieces of information except one of them, so we solve for that, which in this case was trivial because it was already on the left-hand side. Then you plug the numbers in. You're careful about the sign of the rate of change that's given to you, whether it's positive or negative. Oh, there we go. So those are all the parts that I just talked about. Use geometry, differentiate with respect to time, solve for the unknown rate of change. Okay, so here's another. We'll do another one. And this is an example in your book, but it says that at a sand and gravel plant, sand is falling off a conveyor. So here, let's draw a conveyor. So here's the conveyor, and there's sand on here, and it's going down, falling in there. falling off a conveyor into a conical pile at the rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? Okay, that's a lot of information. You can be overwhelmed, but let's just kind of work at it. So like in physics, these problems, it's good to draw a kind of schematic. So here is our conical pile of gravel. And it says that the pile is increasing at a rate of 10 cubic feet per minute. So what we can say is that the increase in volume of the pile with respect to time is equal to 10 cubic feet per minute. So it's volume per unit time. And it's positive because it's getting bigger. Okay, so here we have the diameter of the cone. That's the base. And apparently it's changing such that the diameter of the base of the cone is approximately 3 times the altitude. So I didn't draw this very good, but so there's the height. That's the altitude. So from that we can say that the diameter is 3 times the height. And it's asking for what is the rate of change in the height of the pile. So what we're trying to find is what is dH dt. That's the unknown. The other thing we need is what is the volume of a cone, circular cone. So we go to our, actually it's not in here. Does anybody remember the volume of a cone? And then an SOL requirement? No, I don't know if that's an SOL requirement. So let's think about it. So the volume is, so what do you, it's probably a function of the diameter, right? And it's probably a function of the height. What is the shape of the base of a cone? Circle. What is the, so what is the equation for the diameter? Well, the area of a circle, we just talked about that. It's pi r squared. So it's probably going to be involved diameter squared. What we might want to do is actually use radius there, just because we usually use pi r squared. So I'm going to change that to r. Okay, r. So it's probably r squared, right? And the height, it's probably linear with the height because the sides, you can see how the sides build up as like a line. And probably pi is involved because it's got a circular base, so there's probably pi somewhere here. And we divide by a number. Does anybody write a number we divide by? If we just use pi r squared h, that would be like a right circular cone, which is like a can, or like kind of like this, that's actually symmetric. So in this case, it's going to be less than that. That's why you divide by a number. So we'll do a vote here. So it's a possible, it's either 2, 3, or 4. Okay, so how many people think we divide by 2? How many people think we divide by 3? How many people think we divide by 4? Okay, so it's not 4. You're right about that. Turns out it's 3. Okay, because if it was 2, it'd probably be like a triangular cone. So you'd have it like this. But in this case, it's getting smaller in 3 dimensions. So in 2 dimensions. So anyway, that's the volume for the volume for the right circular, or no, whatever it's called, a cone. Okay, so that's our geometric relationship. The problem is that we've got 2 variables, and we can only do this with respect to, well, we could actually do it with, you could use the product rule here, but there's an easier way. In this case, you can use this information, which says the diameter is equal to 3 times the height. The diameter is 2 times the radius. So you get 2 times the radius is the height, or the radius or the height is equal to 2/3 the radius. Okay, so this was given in the problem. That's the definition of diameter relationship between diameter and radius. Solve for h. I could solve for r, but because I only have to, it's easier to do the math. Okay, so if we plug that in there, you'll get pi r squared times 2/3 r divided by 3. And so if we simplify, we'll get 2 pi r cubed over 9. So given the relationship between height and diameter, the volume is this relationship. So what do we do? So now we've done, there's the geometry. The next thing we do is we take the derivative of that expression with respect to time to relate the rate of change in volume to the rate of change in, and you're saying, well, you're going to solve for radius, right? They ask for height, but once I get radius, I can relate that as well. Maybe I should have done h. Well, it doesn't matter. Because think about it, if I take the derivative of this expression, dh dt is going to be equal to 2/3 dr dt. So if I take the derivative of each side here, there's no tricky differentiation. So once I get dr dt, I can then get dh dt. So we'll just keep it at r. So we take the derivative with respect to time of v, and we take the derivative with respect to time of 2 pi r cubed over 9. And the left-hand side just becomes dv dt, the rate of change in volume with respect to time. On the other side, you get 2 pi over 9 times the derivative of r cubed, which is 3r squared. But because this is r and this is t, you have to have the dr dt. So you can see now I can calculate what they're asking for. Well, they're actually asking for dh dt. I'm going to calculate dr dt once I know that. So we're going to, this is the thing we're asked to solve for right here. Okay. So we know what dv dt is. That's 10 cubic feet per minute. Wrote that down here. And it says, at what rate is the height of the pile changing when the pile is 15 feet high? So what I can do is say when h equals 15 feet, r is equal to, if I solve this for r, it's 3/2 h. So it's 3 times 15 divided by 2. Get my calculator out. Maybe I should have done it the other way. Should have solved for h. We'll do it the other way, just to show you get the same answer. Okay, so 3 times 15 divided by 2 is 22.5. So the radius is 22.5 feet. So that's my radius where I want to do my calculation. This is my dv dt. So all I have to do is solve for this. So if I solve for that, I'll get dr dt is equal to, let's simplify that. So we'll multiply by 3/2. What I'm doing is I'm trying to solve for this. So I'm going to multiply by the reciprocal of that. The reciprocal of 2 pi or 3 is 3 over 2 pi, and the reciprocal of r squared is 1 over r squared. And then I multiply dv dt. So all I've just done is move stuff around. This goes to the top, this goes to the bottom, this goes to the bottom, this goes down, and I've solved for dr dt. And so now I just plug the numbers in. So you get 3 over 2 pi times 1 over r, so that's 22.5 feet quantity squared times 10 cubic feet per minute. So 3 times 10 divided by 2 divided by pi divided by 22.5 squared is dr dt is 0.00943 feet per minute, and so therefore dh dt is 2/3 of that, 2/3 of 0.00943 feet per minute times 2 divided by 3 is 0. Let me move this over a little bit. 0.0063 feet per minute. So that's how quickly the pile is growing. Okay, now I'm going to redo it in the other variable, which was probably the easier way of doing it. You'll see that I get the same answer. I'm pretty sure that's the right answer. So let's go back. What we're going to do now is we're going to, instead of starting here, we're going to write the volume again. The volume is equal to pi r squared h divided by 3. What I'm going to do now is I'm going to actually use the other substitution. So it would be r is equal to 3/2 h. So what I used was h is equal to 2/3 r. The other one is r is equal to 3/2 h. So if I do that and I plug that in, I get pi times 3/2 h quantity squared. So for r, I put in that times h divided by 3. So you get v is equal to 3/2 pi, 3 squared. Yeah, we got to square the 3/2. So you get 3 squared, 2 squared, pi you don't square, times h cubed divided by 3. So 3 squared divided by 3 is just 3. And 2 squared is 4. So you get 3/4 pi h cubed. Okay, so that's the same thing that I did before, but I solved for r instead of for h. So now I've solved for h. Now I take the derivative. I take the derivative of that with respect to time. So take the derivative of the volume with respect to time is equal to the derivative with respect to time of 3/4 pi h cubed. So dv dt, rate of change in volume is equal to this 3/4 pi times 3h squared times dh dt. Yeah, that's probably the better way of doing it. But to prove, I'll show that you get the same answer, just longer. Okay, so if you solve, in this case, instead of for dr dt, for dh dt, what you'll get is that dh dt is equal to, okay, so you've got 3 times 3, which is 9. So let's replace that with 9. So you'll get 4/9. So they take the reciprocal of that. Pi is in the denominator. H squared is in the denominator. And we multiply by dv dt. So again, what I've done to solve for this, I multiply by the reciprocal of that, the reciprocal of that, the reciprocal of that. And at this point, I can actually plug the numbers in a little easier. So I get 4/9 times 1 over pi times 1 over h. H is 15 feet. So 15 feet quantity squared times dv dt, which was 10 cubic feet per minute. And if I punch those numbers in, I should get the same answer that I got just a second ago. Yes, I did. Thank goodness. Okay, so you see I got the same answer. Just the first way was a little bit longer. It helped. It made one thing easier and made a lot of other things hard. Okay, so that's a little complicated. But the basic idea is the same. We look at the problem, we find out what rate information is given, we make sure the sign's correct. We try to come up with some geometric relationship, which in this case was volume instead of area. We used some additional information from the problem to make the equation in one variable, whether it was h or whether it was r, it didn't make any difference as far as the answer is concerned. So that was the geometry that related the height and the diameter. And then we took the derivative of the simplified geometric relationship, solved for the unknown rate of change. At that point, to be able to solve the problem, everything else has to be given in the problem statement, which it was, and you plug the numbers and you get the answer. Okay. So let me give you something. We'll work on this one. I've got 6 problems here. So these, like I said, we're going to spend a fair amount of time on this. Just because some people either get it, or it's usually they get it or they don't get it. So I'm aiming for more people getting it this year. Luckily, there's only one problem on the test that's related to rates. But this is more from my personal challenge to try to get you guys to understand this stuff. And if you guys don't get it, I'm giving up. No, just kidding. I'm retiring. Oh, did I leave one for? Yeah, I did. Okay, so let's look at the problem. Number 10. A rectangular swimming pool with the horizontal bottom is being drained. If its length and width are 25 feet and 20 feet, and the water level is falling at a rate of 1/2 foot per minute, how fast is the water draining? So this is like the problem we just did, actually easier, because it's, instead of adding to a conical pile, we're removing from a rectangular parallel piped. You know, it's just a swimming pool that's with a constant depth, which makes it easier. So the first thing that we did was we had to come up with some relationship. So if I have basically what I have here is I have something that looks like this. So it's a boring swimming pool with no deep end. And the dimensions are 25 feet in this direction and 20 feet in this direction. And this is the changing dimension. So that's the height of the pool. So what is the volume of water at any instant in time in terms of the 3 numbers that I've given you? So let me ask somebody. Mark, what is the volume of that pool? So go ahead. Yeah. So the volume of the pool, and because it's, so it's just height times width times length, or whatever the 3 dimensions are. So in our case, volume is equal to 25 feet times 20 feet times h. So that's our geometric relationship, which is pretty easy. It says the water level is falling at a rate of 1/2 foot per minute. So what? So something equals, and the question is, so it's 1/2. There's two questions to answer here. So Kelly, what variable is changing up according to our diagram?
The height.
Right. So what is equal to 1/2 foot per minute? What is the derivative? Derivative with what with respect to what? Derivative. Yep. Yep. So dH dt is 1/2 foot per minute. Okay. So Cassie, should that number be positive or negative? Right. Yeah, because the height is getting smaller. And that makes sense too, because if the height gets smaller, or if the rate of change in the height is getting less, then this, when we take the derivative, so now what we can do is we can take the derivative of the geometric relationship, which you would get dv dt is equal to, if you multiply these together, you get 500, I think, right? 25, yeah. So you get 500 feet squared times dH dt. And because this is negative, this will be negative, which makes sense because the volume is getting smaller. So now that we have this relationship and we've defined what's going on, and it turns out that the rate of change in volume doesn't depend upon what the height is. So at any point, they don't tell you what the height of the pool is, I don't think, because it's not needed. Because I only have h here, so I just get dH dt. If it was involved h squared, then I have to know what the height is, but it's not. So now you just plug the numbers in. So go ahead and plug the numbers in. Actually, the number. There's only one number. And calculate it, which actually you can do in your head. Right? Hopefully everybody can do half of 500, which is 250. So it's negative 250 cubic feet per minute. So that's the rate of change in the volume with respect to time. So that's all there is to that one. That was pretty easy. But it does, it does show you the steps that are involved, which is finding some geometric relationship. Okay. Well, actually, the next one's very similar to the cone one we just did a minute ago, except in this case, the cone is getting smaller instead of getting bigger. And also, it's given different information. So let's, why don't you draw a picture and see if you can put as much information on there as you can based on the problem statement. So draw a upside down right circular cone to make an icicle. You don't have to show it in 3 dimensions. Here's where it's hanging from. Here's your icicle. Okay, here it's dripping down there. And remember, the volume of a right circular cone is pi r squared h divided by 3. Yeah, actually what's happening with the icicle is it's getting longer, but the diameter is getting smaller, because it says that the height is increasing, but the radius is decreasing. So it's not like the pile, which is getting bigger in both directions. So after you've done the drawing and put some dimensions on it, see if you can it says that at a certain point in time, the height is increasing at the rate of 1 centimeter per hour. So see if you can figure out what that derivative, that's the derivative of something with respect to something. And there's a sign, is it positive or negative? And then you'll do the same thing with the radius. The radius of the base is decreasing at 1/10 centimeter per hour. So try to represent that information as some given information as a derivative. And then the final question is the volume of the ice increasing or decreasing at any instant? And then they're asking for the at what rate. So the tricky part here, which you probably are not going to figure, well, you might be able to figure it out, is there is no relationship between height and radius. So we can't simplify this down into one variable. So we actually do have to use the product rule on this. So let me see if you give this a try. Take the derivative of this relationship with respect to time and use so you'll have 3 pi and then multiply it by the derivative of this product. So remember, it's the derivative of the first times the second plus the other way around. And in this case, both parts of the derivative will be implicit. So before we had x times, if we had like x squared times y, we would take the derivative of x squared and multiply it by y. And then we take the derivative of y and multiply by x squared. In that case, the x was just a normal derivative. The y part was implicit. But in this case, when we take the derivative of this and multiply it by this, you're going to have to use implicit differentiation. And when you take the derivative of this, you're going to have to use implicit differentiation when you multiply by that. But see if you can think about how you would do that. I'll give you a few minutes to try to put out as much information as you can glean at this particular point. And then I'll let you know what the answers are. Oops. The one advantage of double vision is you never forget your glasses. It's like somebody slapping me up the side of this, I can't do this and say, oh yeah, things are normal. Okay, so I'm going to start giving you the answers in the order that I asked them. So there's my information. So I got the distance from the center of the cone to the edge is the radius. And we're looking at the specific case where the radius is 2 centimeters. The height is from here to the bottom, and that's 15 centimeters. And it said that the rate of change in the radius of the base with respect to time, or just the rate of change, is negative, decreasing 1/10 centimeter per hour. And the height was increasing at a rate of 1 centimeter per hour. So that's all the given information. Now the derivative, when you take the derivative with respect to time of the volume expression, you're going to get dv dt on the left-hand side, and you'll have pi over 3. And then what we do is we take the derivative of the first, which is 2r dr dt, times h. So that's the derivative of the first using implicit differentiation times the second part of the product, plus the first part of the product, which is r squared, times the derivative of the second, which is just dh dt. So that's how you end up with, that's the differentiation of this product. The derivative of the first implicitly times the second, plus the second times the derivative of the first implicitly. And now you can see that we have all the information to get the answer, to find the rate of change in the volume. So, we might as well just figure out what the value is, and then we can say whether it's increasing or decreasing. Okay. So you'd have pi over 3 times 2 times the radius, which is 2 centimeters, times dr dt, which is -1/10 centimeter per hour, times the height, which is 15 centimeters. So that's the first part. The second part is the radius, which is 2 centimeters, quantity squared, times dh dt, which is plus 1 centimeter per hour. And if this is the whole thing here is positive, then it's increasing. If this whole thing is negative, then it's decreasing. That's how you answer the first part of the problem. So let's plug that into our calculator. So it's 2 times 2 divided by 10 divided by -10 times 15. So I'm going to actually put the numbers down. So the first term is -6, and then the second one is 2 squared times 1, which is 4. So you can see it's going to be negative. So you end up with -2 pi over 3. So -6 plus 4 is -2. So you get -2 pi over 3 cubic centimeters per hour. And hopefully that's the right answer. I can't remember what the right answer is, but if you don't see a mistake, I'm assuming I'm right. Your initial thought was, well, the length must be the length's getting longer, a lot longer than in terms of the actual magnitude. The height is getting 1 centimeter per hour, whereas the radius is only 1/10 of a centimeter. It's getting smaller. So you think that it was going to actually increase the volume, but it kind of makes sense that it should be decreasing because it's probably getting longer because it's dripping. You're losing water by melting. Okay. So let's just look at the next one to see what this one is. Okay, this is going to be similar triangles. We still haven't got to any kind of ones with well, actually what I'm going to do is we'll come back to that in a minute. I want to find an example that I've got that has to do with triangles. Oh, that's quicker done than I thought. I'm going to make up a problem. Okay. So we'll set it up and then we'll talk about it tomorrow. So let's so what we have is we have a house, and we have a ladder. We have this ladder sitting on the side of the house, and what happens is the ladder slides away from the house. The top of the ladder goes down, and the bottom of the ladder slides along like that. So some guy's standing on here, and he forgot that it was ice on the sidewalk. So he climbs up here, and all of a sudden it goes zoop, crash. And so while he's falling, he's thinking, I wonder how fast that ladder is moving away from the wall. So what we're going to say is that the distance of the ladder, the bottom of the ladder from the wall, is, we're going to call that x. And the distance of the ladder from the floor is going to be called y. And we're going to say the ladder is 10 meters long. So the length of the ladder does not change. What changes is how much this distance is going to get smaller, this distance is going to get longer. So if the bottom of the ladder is moving at 1.5 meters per second away, and x is equal to 4 meters, at what rate does the ladder slide down the building? So that's the problem. And the procedure will be the same thing. We're going to use a geometric relationship between this distance, that distance, and this distance. This does not change, so the hypotenuse doesn't change. But both x and y are going to change. But it is a right triangle, so this is going to be an example of using the Pythagorean theorem as our relationship between the two variables. In the previous problems, we've related height and radius to volume and radius to area. In this case, it's the Pythagorean theorem example. So I'm not going to assign any homework from this section until tomorrow. So for study session, you can be working on your physics chapter 4 homework, right? So Savannah, I'm going over to Rockbridge today. So I think I'll call your sister Savannah and see what she says.
I hate her.